go. Yes, and as somebody said or noticed, I do have the laptop plugged in. So it's all good, right? We'll at least have enough juice for that. So this isn't necessarily what this picture's for, but if you, in the daytime, if you were to get above the Earth's clouds, the Earth's atmosphere, I guess I should say the Earth's atmosphere, it doesn't have to have clouds. If you were to get above the Earth's atmosphere, looking towards the sun, it would be pitch black with the sun just being like a star up there. Okay. And actually, it's one of the things we talk about in meteorology, is that the Earth's atmosphere is what kind of makes our blue skies blue when the sun shines through the Earth's atmosphere. But this chapter is going to kind of talk a little bit about historically, kind of the thought of how we came to know what we know, but we don't know what we don't know. Right? So one of the things is you've probably all heard of the scientific method. And I'm going to kind of end this chapter with talking you through experimentation, or observations, experimentation, hypotheses, testing, blah, blah, blah. Your hypotheses can be elevated to a theory. But in general, thinking scientifically, actually, if you read your textbook, I should give it more stock than that. Thinking scientifically wasn't always the way people thought. It was kind of like more, they might see something happen, but they assumed that there was no explanation behind that something that happened. Okay, a ball rolled from point A to point B. Okay, there's no explanation. You know, we know that there was a force that made that ball move. Okay, so based upon observations, and it's kind of common sense. So early on, cultures have appreciated the movement of stars, seeing different sets of stars as the Earth orbits the sun. You know, and it's been important to tell time of year, time of day. Okay, there are all sorts of cultures based upon the moon and what the moon can do for you. Okay. The Stonehenge, and I didn't bring in it, but your textbook, this edition has a really cool picture of Stonehenge. So, like, for instance, that was a monument put up to appreciate the, I don't know if it's the equinoxes and the solstices, but those important points when the Earth is at these important points in its orbit about the sun. It's just amazing. So, you don't see United States on this map. Right, we're a relatively new culture, no surprise there, right, compared to these older cultures. So a lot of our science actually is embedded in this region. Your textbook, I think, does a good job. It's kind of a sad job. By the way, this region, a little unstable these days, okay? And your textbook actually talks about the instability and what that consequence that had with regard to knowledge. A lot of times, the names of stars I can't pronounce. Why? Because they are like Arabic. Like, I don't know. A lot of stars that begin with letter A. Okay. And that's not an accident.
That was beautiful in the book, this picture.
Yeah, I agree. The text,
that library.
The Library of Alexandria, that was creamed. I can't remember which troop came in and just wiped it out. But I think King Alexandria, which was a student of Aristotle, I think, said, all right, you know, knowledge is king. Let's go ahead and gather all the knowledge we can and put it in this library. That king was overthrown, and guess what happened to the library? Okay, and then some of this remnants was tried to recapture, and the Muslim culture took it from there to try to reestablish a central location for knowledge. Today, we would call that the internet. You know, crazy times. It's like passing the baton, though, you know. I just love science because we don't have to reinvent the wheel, so to speak, right? So just a little bit about the history and who did the conquering and who did the surviving. So when I go to test you, I don't necessarily ask you names and dates and things like that. But I do think it's interesting, and I think the book did a great job. So I'm going to go ahead and write on the slide. The word planet means wanderer. The wanderers.
Did you put that in, is that a new slide?
Oh, what's your next slide? Just that one? Okay, it must be. Well, we'll see in a minute. So the planets, the word planet means wanderer. So here's the deal. The constellations are always where they are, but the planets will move against the background constellations. And honestly, it's this wandering of planets that we need to explain when we take an overall look at our solar system. Okay. So you guys don't have this one anywhere? Okay. We'll be talking more about the planets. What's that?
I just wrote about it.
Oh, cool. We'll be talking more about the planets. And right now, let's see if we can remember how this is. Right now, if we're able to go kind of set up like 8:30-ish or so, we will still see Saturn and Mars, PM. In the morning, finally I listen to a podcast, I'm like, that's why. I get up in the morning and I keep trying to see Venus and Jupiter. And Venus, I heard somebody say, oh, did somebody drop a key? It's a pretty key.
Yeah, it was sitting up there, and when you...
Oh, when I knock this over? Okay, well, let's do that.
Let's try not to break anything this way.
No guarantees. That looks kind of bad right there. Venus is in the morning sky, but it's really low. Sometimes Venus, and I'm pretty sure like a year ago, the last fall, Venus was like just shining, just. And it usually doesn't get very high. It kind of has a short tether, but. So in the nighttime sky, or in the morning sky, we should be able to see Venus and Jupiter. All right. And Mercury, shy little guy. It's always hard to see. Okay.
Don't need to write those down.
No. But did you write down planets and wanderers?
Yeah.
Okay, that might be good. So, way back when, I brought in these figures of these guys. Of course, they're not photographs or anything, but they're busts made of Plato and then Aristotle. Okay, so as we talk about the scientific method of looking at, of observing things and thinking that we can explain why those things happened. That's part of the scientific method, and that goes beyond mysticism. Okay, and so I want to say Plato and Aristotle made movement in that area. So let me go back. What did we call that? The heavens, the whole hollow ball thing. Remember?
Celestial sphere.
Yeah, that's what I was thinking of, the celestial sphere. And for the longest time, up until, well, there was hints at that not being the case. That actually, that all the stars were the same distance from the Earth, and that stars orbited the Earth. Okay, but for the longest time, that was the model that they really thought was the case. So the whole celestial sphere, okay, we can kind of think of those stars on the celestial sphere. You don't have this slide either? Really?
It's all the ones that say from chapter 2 on the bottom.
Okay. Well, thank you. Well, then just listen. And I'll try to tell you what you need to know. The title's a good thing to write down. The title kind of slums up. Because what I'm going to say is those wanderers, I said, right, planet is equal to wanderer. You know the Big Dipper's the Big Dipper. You know the constellation of the Scorpion is always going to be like that, okay? But the planets kind of wander, okay? Okay, they kind of wander, but they're always on the plane of the ecliptic. Okay, so if the celestial sphere model stayed in place, okay, you could say the whole rigid stars orbit the Earth, right? It's kind of creepy. But what's up with the planets? Okay, you can't explain that. So the title should do it for you. Celestial sphere model, or the fact that everything orbits the Earth, like they do everything except for those wanderers. I can't remember. I will email these slides to you. I think it should be about done with my chapter 2 slides. Okay. But because there is something that, a term on here, okay, apparent retrograde motion. So I'm going to email these to you. If I don't, somebody has to remind me. Apparent retrograde motion. Okay, that is, let's see, retrograde is somebody is retro, they're a little backwards maybe? I don't know, I kind of like retro. Okay, but that's what retrograde motion is. It's a backward motion as to what you think it should be. So here we go. This is normal motion. Normal motion of the planets against the background stars from night to night. This right here is retrograde. And I'm going to try to explain why. Okay, so Mars and the planets tend to look like this. Then all of a sudden they look like they kind of do a loop-de-loop, and then they'll go back to their normal again. Okay? Phew, not a chapter 2 one. Okay, so Ptolemy, we're still not there yet. And I'd like to say, when Ptolemy came on the scene, everything sort of cleared up. But Ptolemy is kind of, I'll put this whole slide up here. Ptolemy is kind of accredited with being the last of the celestial sphere, the last biggie when it comes to thinking of the Earth in a hollow body and everything orbiting the Earth. So whenever somebody says the Ptolemaic model, think celestial sphere still. Ptolemaic model still puts the Ptolemaic model, I know they pronounce it PT, the Ptolemaic model, that P is silent. The Ptolemaic model, okay? Still think that they're putting the Earth at the center and stuff orbiting the Earth, okay? Ptolemaic models are very kind of pretty. They're complicated though. And so there you go. So the Ptolemaic model did a bunch of gyrations, kind of added to maybe stuff orbiting the Earth. It had the planets. What you're looking at are the planets orbiting the Earth, or a planet orbiting the Earth. But as it orbits the Earth, well, we know planets don't really orbit the Earth, right? As it orbits the Earth, okay, at some point, so this is the normal motion of the planet. Now, I'm not saying that the planets orbit the Earth, but Ptolemy did, okay? Okay, at some point, it does a little loop-de-loo and goes back again, okay? And it's this loop-de-loo that can explain retrograde motion. Now, there's one thing, if you've ever heard of the KISS principle, keep it simple, stupid. Okay, science believes in, and it's actually formally called, I think if there's a slide coming up, Occam's razor. If you're trying to come up with, if you're trying to describe the situation and you have to do so many strange things to ultimately come up with something that explains your observations, it's like playing Twister. Okay. Something's wrong with how you're trying to explain it, okay? So this failed the Occam's razor, or the keep it simple, stupid model. So this is what Ptolemy thought. Again, do you see the problem with this? The planets orbiting the Earth. Right, okay. Now Copernicus carefully switched gears. Actually, he wasn't the first to propose that, that he wasn't the first to put the sun at the center. Okay, but he kind of started the revolution. And I think your textbook says when Ptolemy came out with his no guys, you're wrong, putting the sun here and putting the Earth orbiting the sun, the planets orbiting the sun, okay? I don't know what he did with the stars, quite frankly, okay? He had to be careful because he was bucking the establishment. So here's the but, though. Copernicus, he could actually, I'm going to try to show you how if we go ahead and put the center at the center of the sun and have the planets orbit the sun, I can explain retrograde motion. And we can. But his model still didn't quite, still couldn't quite set your clock to when you would see the planets coming in the nighttime sky next. There was still something wrong. And this slide actually tells you what needed to be fixed. Okay, what needed to be fixed was the shape of the orbit of the planets. Okay. He was still really kind of fixated with all planets orbit the sun in a circle. And what we're going to see is Kepler finally broke out of that. And it's not as perfect as a circle, but these ovals, that's the shape of the planet's orbits about the sun. So Kepler kind of broke that out. Okay. Do you guys have this slide?
Mm-hmm.
Oh, good. So Copernicus put the sun at the center of our solar system. And I have a slide to kind of show you how this works. What I tell students, and this isn't on the slide, but picture yourself, I don't know if this works for you. Okay, so you're driving in the left lane, a little bit faster than the people driving in the right lane, okay? So you're coming up on somebody and you're going faster, okay? If you were to look at this person that you're coming up on, if you were to see how that person, that car, was moving against the background, you would see that person kind of go, you would see that person for a while kind of go like this against the background. Trees, let's just say you guys are out in the middle of trees. So here's the deal. So you would see him kind of go this way against the background. Now as you come up against him, when you're getting close to him, you actually will see that person kind of look like he goes backwards against the background. And then you'll get sufficiently far from him, and then he's going to look like he goes forward. That is what's happening. One of the things Kepler found out is that the inside track, or what's outside of us, is Mars, right? The closer the planet is to the sun, the faster it moves. So honestly, in the thing that I just described, Earth is that fast-moving car, and Mars is that slow-moving car. So I have to kind of like this. So it goes back, now it goes backwards, and now it's going to go forward again. Okay. That's it. So this talks about overtaking the planet. We're going to see that Kepler came up with, say, 3 laws, and one of his laws, I already told you, was the shape, an oval, not a circle, and another one of his laws is that the closer a planet is to the sun, the faster it orbits. And it's not that it orbits faster because its oval is smaller. It literally is moving through space faster. Okay. So I bet you guys must have this one? Okay, good. So the blue planet would be the Earth, quite appropriately. The red planet would be Mars. Okay, and so looking at times 1 through 7, and so not so surprisingly, based upon what I told you, you can see that from, by position, by time 7, that the Earth has traveled more through more space than Mars. It's moving faster because it's on the inner track. So, what your author did, I think pretty good, is that he showed Mars, where we see Mars, against the background sky. So, for instance, we would see Mars in Gemini. Okay, at this is 1 and 1, 2 and 2, 3 and 3, 4 and 4. Okay, so let's look at where we see him, Mars, her, it, next. Okay, this is normal motion. Okay, sometimes normal motion is called direct motion. Okay, position 3 is still normal motion. But you see where position compares 3 and 4? 4 is retrograde. Okay, and actually 5 is retrograde. And then we pick up with 6, and 6 we have passed Mars sufficiently, and it's kind of trailing, that again we see it going, normal. There, you guys look convinced. That's good. I'm glad for it. Okay. All right. Okay. Well, another thing that needed to be explained is this idea of parallax. What parallax is, okay, I think is and I snagged this figure from another textbook. What parallax is an observer at slightly 2 different locations. So the observers would be this man and this woman, okay, both looking at a nearby object and comparing that nearby object to the background. So can you see where I'm going to reveal that top of that tree? For instance, that guy sees that top of that tree against, it's a trajectory thing. Nearby object, tree, far away object, the mountains. Where do you think this woman sees her tree?
In the middle of the 2 of them.
Yeah, I agree, kind of in the middle of the 2 of them. Exactly. It's parallax. Okay. So, in general, we have a guy and a gal at 2 different positions. And that's similar to if the Earth, and we know it is, if the Earth is going around the sun, when we look at those pinpoints of light now known as stars, and we're starting to probably figure that out, shouldn't the position of the stars change? Just kind of like the relative positions of the top of the tree and the mountains. Should we see parallax?
Is parallax like the same as like if you look at one thing, like with both your eyes, and then when you close one, it
yes,
looks different
thank
than
you.
open
Yes,
another? Okay.
yeah, and I'm glad you mentioned that because sometimes I'll have students, if you hold your finger by your nose and blink your eyes back and forth, that's parallax. Exactly.
Okay.
Close one eye and open. You know what I'm saying? Like right now, it's over there. Now it's over there. It's parallax. Something nearby that looks different. Another thing about parallax is if you're like driving with driving a car, and instead of having like a readout of what speed you're driving, if instead you literally have that kind of analog little like old-timey thing, okay, what the driver sees could be different than what the passenger sees. Okay, so that's parallax. So, this idea of the Earth not being stationary, the Earth moving, then you're like, dang, well, how come we don't see kind of different shapes as patterns in the sky? And the answer to that actually is, I can't remember where it is in the lecture, but you don't see parallax if, for instance, if we had a mountain range, or if we had a tree here, clear on the mountains. Picture a tree, a humongous tree that's basically smack dab way out there on the mountains. And picture you're the 2 positions. You're like, at that point, they're both way out there, okay? And you're not gonna see parallax with way distant objects like that. Okay. But, upon careful observation, there are stars that they have to be kind of close by, that as we change our position 6 months apart, we are literally, January, 6 months later, and in July, we can actually see a nearby star will change its position against the background stars. Now, this is not normal. Because if this sort of movement of stars, okay, happened very much, we would just go crazy. Okay? Picture your favorite constellation and think of the stars kind of scrambling. But nearby stars, we do see parallax. And actually, the amount of jump, okay, the amount of parallax we see 6 months apart like that, we can kind of break it down into an angle, and we can use that parallax angle to know the distance to that star. That's later. Okay. So if the stars are sufficiently far away, no parallax. Alrighty. So we had, who'd we have? Well, we had, beginning with Ptolemy. It was Ptolemy, right? And then Copernicus, and then Brahe, and then we're going to have Kepler. So Brahe, if you read your textbook, okay, I think they do a good job. Brahe reminds me of, I think your textbook paints him as somebody who had a lot of money and was driven, but he kind of lacked what we say the skills in the lab. Okay. Awesome toys. So one of the things he's noted for is with his awesome equipment, taking some just crazy cool numbers that positions of objects that could be used to understand the nature of our solar system. So I mentioned Kepler and his 3 laws. Remember, he was the one that kind of broke out the whole circle into an ellipse. And I told you he came up with that. One of his laws says how inner planets go faster around the sun than outer planets. So Kepler came in, was hired by Tycho Brahe. There's Kepler. So before Kepler finally took the whole circle thing and said, no, that's not the right shape, we need to go with an oval, otherwise called an ellipse. That's what Kepler said. They were trying to, you could not ignore, this says 8 arc minutes, you could not ignore that kind of screwiness you get with a circular orbit. He says, we got to do something about that. Scientists don't try to ram their data to fit something, usually. And we're glad he didn't. But to me, it's not necessarily kind of like a prince and a pauper sort of thing, but to me this points out, especially years ago and even now, it seems like people with the money can make it to the universities, the cool equipment, you can say that in anything. You can say people who have connections, even though they can't sing, will make it on the top 40. Like, what? In fact, I've heard scientists lament, it's like the person with the cure for cancer in his or her brain, could be somebody who, from one of these countries that just barely may not make it because they don't have food to eat. So it's interesting. Okay, Kepler. So that would be perhaps a circle. Looks like a circle. Okay, so a circle, you can put a thumbtack in the middle. Okay, take a string out and draw like that. Okay. And ellipse is different than a circle. And I've been calling it an oval. Okay. But the thing about an oval is you can find a center, right? But the distance from that center outwards is not the same, okay? It's got short semi-major axis and long, what we call semi-major axis. But there is an important, and that does end up being important, okay? The way you draw ellipses is that you move your thumbtacks. You have two thumbtacks. Kind of looks like a spirograph, doesn't it? You have two thumbtacks, and you take your string and you draw it around like that. Now those two thumbtacks are what we call foci. And I told you that the planets orbit the sun in an ellipse, right? Or in a oval. Same thing. And you know what? The sun is located at one of those foci. Isn't that cool? So the planets orbit the sun. The sun's at one of those little tanks. It's a sweet point for an ellipse foci. So there are two foci in ellipses, and kind of the crisscross you see makes sense to me. Kind of the crosshairs that go through the center. You have the minor axis and the major axis. This talks about ovalness, eccentricity, otherwise known as ovalness. Ovalness. That's what eccentricity is. Okay. The more flattened it is, it gets 0. The more like it is a circle, it gets eccentricity of 1. Okay, the ovalness. All right. So before I leave, I want to kind of bring together one of the things we've talked about. So I told you that the sun is at one focus. So I'm going to go ahead and that's my symbol for the sun, okay? And so that black line that pencil's drawing out could be us orbiting the sun. Now, it's a little eccentric now. But do you guys remember we talked about something called, this could be the Earth at aphelion? And what would this be the Earth at? What do we call that position? Very good. Perihelion. Perihelion. Yep. So that's kind of where we're going with this. It's amazing. Kepler. Hats off to Kepler. So the eccentricity value of these two ovals are given, or ellipses. The top one's a circle, and with the eccentricity of 0. Okay, and you can see like a moderate eccentricity. This might be, and it approaches 1. So this might be, I don't know, 0.8. And this next one down here is even more eccentric, 0.9. Well, let's take a break, shall we? And let's go for 35 after. And how are we doing for slides? We're going to make it? If we don't go to it. Oh, yeah.
3.5 pages plus 1 month on this page.
Yeah, I think we'll be good. So probably plan on one segment instead of 12 segments. And I'll get something to eat. I'm with gas. How late does Casey stay open?
24 hours.
24 hours. The one out here is open 24 hours?
Because like in Burlington, that closes like 11.
Well, they might close, but pumps are 24 hours.
Okay, so you can start.
Yeah.
Okay, that'd be no fun.
Yeah, the Casey's down by the mall is open 24 hours.
Is it?
But they revisit